Welcome back everyone. It's time we start talking about the applications of some of the non-stationary time series models. Basically the estimation techniques of non-stationary models up until we'll cover till artificial neural networks. Then we'll come back to non-stationary discussion again because we still have to cover bilinear models, Markov switch and others. But it's good to split the discussion into two so that we can go slow and understand more clearly. So the first problem is we are given autoregressive 2 process. We need to simulate the model for t equals 40 observations where the initial value is, so we are given an initial value. We want to show the model converges to the equilibrium point at y equals 1, derive the result analytically. So this is the first nonlinear equation model where the nonlinearity, we are trying to show that in the AR2 process, which is a nonlinear model, the process will converge at an equilibrium point y equals 1, which is the first in the discussion. We said that eventually in an autoregressive model, when there's a linear system of equation, we expect convergence, and we expect a property of linear models is that a magnification and dampening follow the same length. So if you have 2 periods dampening, you might expect 2 periods magnification, but when this property deviates, which that calls for a nonlinear model. So if after 2 periods of dampening you have 40 periods of magnification, that is not a linearity property anymore. That becomes a nonlinear property. And then we have to move on to nonlinear discussions. And the first thing to do in nonlinear discussions is to split the model according to some conditions. That is what's shown in number B, where the following process converges. So this process here converges after 9 period cycle for threshold point for the autoregressive parameter with threshold point is less than 3.05, or which we also known as omega, or when the threshold point for threshold point greater than 3.05, this is where the convergence happens, or this is the equation. So first we have a 9 period cycle, and so this is what we were talking about in theory to begin with. And this is page 36. So if we go to page 2, so a linear model, we showed that what the linear model looks like. Exactly, this is what we are trying to cover now. But then we talked about limit cycle. The second one is limit cycle, and in limit cycle the diagram looks like this. You see convergence happens in the outer portion of the process. Then we talk about strange process, strange attractors, when though convergence happens at the outer region, we see inside the region there are some that the process becomes chaotic. However, at all cases some convergence is captured after a certain period of time if we can specify the model properly. So this is strange attractors contrasting to the limit cycle, and then we talked about multiple equilibria. So in multiple equilibria, nonlinearity is given by a error correction model, which is a cubic with 3 roots, and the histogram shows that yet most of the population is located in the stable equilibria, which is 0.1, and inflection points are non-stable equilibria, which are not 0.1s, and they have little so nonlinear or the non-stable areas will have less concentration. So basically all 4 models are trying to tell you that after a certain period we can expect some convergence, if the specification is properly given to us. So this is what we'll see. Let's start with the autoregressive, general autoregressive process. The first problem, there is no local function here because we're not optimizing anything here. First, as we always do, all true in R, all true ls, all list, which is short for list, list all true, list equals ls all true rm. So we remove everything, then graphics off. So let's start with the stationary time series. We have 40 observations in our question, and the initial value is 0.1. We'll start with, we're gonna do a loop for each observation, and equilibrium point is 1. So let's forget about the loop first. Let's set the equation, but let's set the initial condition first, which is 0.5. Initial condition is 0.5 plus zeros, t rows, 1 column in R 0.5. Then we replicate t, replicate 0 t times. Why? Because we want to store our data, and we want our system to follow, well, the initial value. So we want to store our data here. So we, at the zeros, we basically create initial values up until t, columns. So up until t columns, we are creating the initial value. Because there's only 40, we don't need to specify, storage. Not necessarily only 40 times this iteration will run. So initial value, we take initial value, and then let's think about the equation, which was simply 0.9, 0.7 y minus yt, then yt minus 1. In place of t, we will put I, right? And yt minus 0.6, yt minus 2. Very simple equation. Now let's start the loop. Because it's a AR2 process, s is equal y equals s plus t equals s plus 1. So we'll start with 3 for y, for I equals 3 up until the last of the observation t, for I in 3 to t. For I in 3 to t is the question, is the condition. Then the equation, in place of t we put I, right? 0.9, 0.7 yt minus I, 0.6 yt minus yt minus 1, yt minus 2. Very simple. Okay, and yeah, this is the initial condition that is set, because this equation will follow the initial value. Why not? Is important. So there you have the equation. Then we plot the graph, and so we compare the initial value with time. Then we compare the initial value with t minus t minus 1 lag, right? Yeah. Initial value with the lagged parameter, or t minus 1. So we have the regular autoregressive linear equation. Now let's talk about the limit cycle. And the limit cycle suggests that after a certain period, the system will converge in the outer range of the the system will converge in the outer range of the convergence region. So there is a 9-period cycle which is conditioned with two situations, 2 omegas. So we need to set these conditions, where for this equation is only valid for y lag less than this value, lag greater than this value. Let's see how this is done. A very simple problem again. So we'll start with limit cycles. We'll start with t equals 100 observations, just because it's good to start with a particular initial value. Then we can reduce our data. We remove that, no problem. So we set our initial value, which is again 2 plus zeros, t rows 1 column, because y2, it's a 9 period cycle, right? Oh, because yeah, we are talking about 2 lags, so we are creating initialization from 2 to plus zeros, and will be added to t plus 1 because there is a condition here, and basically we might not need our values to get below 2, that's why. So 4 is a 9 period cycle and we have lags up until 6. So for the first equation, we'll start with s plus 1, 7 to t, but let's not look into the loop now. Let's just look into the main equation. First logic, if. So if the first condition, if yt minus 2 is less than or equal 3.05, this is our equation that is given in the question, right? No deviation from there. Else the other equation. So if yt minus 2 is less than or equal 3.05, so this is the basic logic. If or else, or should I say if in the condition, then else. Very simple. After that we put that in the for loop because we want this to run we want this to run for 7 to t iteratively. So for t starts from s plus 1, 7 to t. So then we put that in the loop function, and in place of t we just put 1, that's all. So if there is yt minus 1, I minus 1, here we have I, here we have I, here we have I, here we have I. It's very, very simple. And you have the limit cycle generated. Then what do you see in the graph? How do you explain? So we have estimated y, and the only tweak here is that initial condition starts from 2, because t is equal to 100. We want to run 100 times because we haven't been specified how many cycles will be. So we're gonna run it 100 times, okay? And we're gonna start from 2 because we have 2 autoregressive parameters, and we don't want our values to go below 2. So because less than is 3, so we don't need many graph. And so first plot is yt against t, and the second plot is yt against the lag t minus 1. That's all. Then comes strange attractors, which is more fun and a bit more difficult than the previous ones. So we have 4 equations here, where y is output, k is capital, I is investment, s is savings. T is equal to 15,000 observations. So we'll start with 5. We're gonna add 5,000, and we're gonna later discard the 5,000 to reduce the effect from the initial conditioning. So you have 100,000 observations that we're gonna probably generate just 1,000 iterations. Simulate the model for t is equal to 15,000 observations. Where does it suggest that there is 100,000? Well, 150,000 observations, right? No, 15,000 observations. So we have 10,000 number of observations because, well, we take 15,000 and we deduct 5,000, so we're left with 10,000. So we have A representing 0.5, which is A equals 5. I'm sorry, A equals 5 here, right? A equals 5, because we're just gonna look into the equation. Where are we? 37. Let's go back to page 3. basically, well, there's no reason you can put anything, just remember where to put them in the equation. A equals 5, then c equals 20, c equals 20 because, well, just for ease of understanding, what do we refer with c? Generally we refer convergence. So c equals 20. Let's just think it like that. D is called delay is 0.01. E is 0.05. All right. F is 280 because we want to set the equation. So G is 4.5 and there, and S is 0.21. Alpha 20, delta 0.05, eta. So alpha 20, delta 0.05, eta is 0.00001, which this is delta. So now let's start. The game begins from here. T equals number of observations on 10,000 plus 5,000. Then we will deduct the first 5,000. Now we need to store because we have to do it for many times. So, and we have two loops, right? We need to store for y and k. So zeros, number of observations up until number of observations, or replicate 0 up until number of observations. And the initial condition, the first element we are setting randomly, 65 and 265. It really doesn't matter. I mean, just an easy number to remember. Let's start with 65. Anything that you want, okay? Not a big deal. And let's just not think about the loop now. Let's run do the function. So first invest is the equation here. You put the equation here in invest, and saving is the equation here. And then y, capital, and income, output. You put the equations here. No tweaks, nowhere. Now remove the t's and put them with I, because I equals 1 to t minus 1, right? So I equals, because it's a backward propagation, t plus 2t, so 1 to t minus 1. See, very simple. T plus 1 to t, there is nothing called t plus 1 to t. This is a backward propagation. So 1 to t plus t minus 1, or for I equals 1 to t minus 1, then you remain the equation as it is. Simply remove the i's. Very good trick, right? In case of confusing models such as these that starts with a backward propagation, you can just adjust the backward propagation in the loop and keep everything else as it is. And then the result that you have two vectors. Trim the first 5,000. Let's graph. Very simple. You set y against k, see what happens. Then you set y against the backward propagation. Okay, so see the prediction. K against t plus 1. So see the prediction, right? And basically you'll have these what is called chaos, strange attractor. And very simple. Final equation is considered a nonlinear error correction model of the logarithm of real money. Oh, before that there is more. We want to see, in the same equation, we want to see the dependence on initial conditions, right? So number of observations remains same, everything else remains same, everything else remains same. We just, instead of y, we just do, what did we do here? We took y1, so let's do y0. Okay, so y0, and you estimate for y0 1 to number of observations minus 1. The equation is exactly the same. Before the number of observations, oh, we are changing the number of observations. We're doing it for the first 100, just for the first 100. So let's do it for the first 100, the same equation. And you do y0 and you do y1. For first 500, because y1 equals 1, k1 equals 1. Yeah, same thing actually. I'm trying to see if there is actually any difference. No. So basically, for 1 is equal 1 to number of observations minus 1, this part of the equation remains exactly same. There is no change indeed. So we are just trying for less number of observations. We're just looking into 100 observations, and we want to see how the plotting works. Yeah, nothing. We just do it twice. Okay, and see, probably when we do it twice, we will prove that multiple times when we plot this equation against time, when we plot yt against time, we will probably see that depending on initial conditions we are getting different results, and that's what we want, and it's far from convergence. That's what we wanted to prove, because the first 5000 is the risky one, right? So within that element, first 100, without and we have not deducted, we have not removed any of the first initial elements, so basically it will not converge. That's what it will prove. That's all. Then comes multiple equilibria. Okay, this model and nonlinear error correction model, very simple. We have 50,000 observations. Okay, mass is around the stable equilibrium value of 0.1 with smaller mass at 0. And what did we see from the figure? We see that most of the population is located at 0.1 equilibrium value when the system becomes linear. It's not nonlinear anymore. Convergence happens at 0.1. So we have 50,000 observations. Mass is around 0.1. So with our initial zeros value, we add 0.1. Then we need to actually store our data with for u residual, and v the structural residual will have another effect, 0.005. variance is 0.005. So because we are randomly generating this number, we don't have the numbers. V is 0.005, which is variance multiplied to that many random number I want to generate. I mean, we want to generate 50,000 random numbers for V. R norm, random number R norm, and sim. I have generated 50,000 for U, which are full of zeros. I've generated RM, which is my concentration, which is the equation changing real money, changing the logarithm of real money, and that has 0.1 where it the system actually converges. We wanted to replicate, so I mean with zeros and 0.1. that's well. So let's not think about the for loop now. The equation is simply the equation that is here. We write it down. Okay, wherever there is t, I put I. That's all. T minus 1 blah blah blah. Then I put that in the loop function. For I in 5 to number of simulations y5, because this equation goes up to 4. You see, mt minus 4 lags, so s plus 1, 5 observations. And then you have rm, and then you trim it, the vector that you have now, rm vector. You basically change the changing drm, which is level minus lag. That's all. Then you have changing, see, RM, and plot the United States monthly unemployment rate, describe its statistical properties including potential differences in the duration of expansion and contraction. And now we are going to use it to, well, this real money is gonna we are gonna use it to plot where frequency is plotted against the midpoint, right? Frequency is plotted against, these are the histogram RM 51. This is just a histogram. I'm creating a histogram here because the question suggests me to draw this for the whole period, right? So there are 51 periods, I assume, and so I'm creating a histogram of RM for 51 periods. That's all, very simple. Histogram with 51. It will have, I'll just do 51 times. The whole thing will be congested to 51 histograms. Good, beautiful. So that solves the first problem, and there was not much, I must say. Next, we talk about the sampling properties of the LST linearity test, or basically we are gonna talk about the threshold models or TAR models, where in this example we'll combine the specification of the threshold models, estimation using maximum likelihood, and hypothesis testing, and data we will do through simulation. So let's actually combine everything. This exercise is based on Monte Carlo experiment on Lukonon, Saikonon and Terrasavarta, where the data generating process was yt 0.5 yt minus 1. So this is AR1 process with omega t equals, as you know, the exponential, this is the, what should I say, objective function or the logistic function, the function that is unseen in, or the hidden layer in artificial neural network. So the parameters, initial values of the parameters are given for betas and for gammas, and we want to do the replication 100,000 times. So start with t is equal to 100 samples. I want to compute the size of the linearity test, assuming the nominal size 5% and the size adjusted power function. So I want to I just want to start with the test, and consistency property I want to test for the consistency property, and I want to show the improvement in the power of the test when I impose a restriction on any order in the auxiliary equation. Remember, power of the test increases when we include a restriction in any order. Then we replace the L star model with star model in data generating process and do again, and then we specify the weighting function by S star and show the model for this, again imposing restrictions. So there's quite a lot of steps in this problem. It's better we go back to page 9 where we have the theories. So first of all, these are the models where mostly we use is L star in threshold, as we can remember, and then a quick review is that they become linear when there is no so D is delay, C is threshold, and this is the adjustment, right? How quickly the model adjusts to mean. Or the models adjust, and if that is 0, it means the system is linear. That's what we generally test, and we estimate all these parameters, but generally we don't estimate D. So we do a grid search to find D that maximizes the log likelihood function. And when we can estimate, we have estimated parameters of D as well as C and omega t, everything, then we can simply do linear regression with our system to estimate the parameters. And in terms of testing that we are right now we are doing Lucanon, this is the element of interest that we are talking about, right? And we take three orders. With the three orders we represent a cubic equation for our weighing function, and based on the test of our linearity we have the regression equation of from omega t we have this regression equation of yt, and generally under the null, I mean, how do we use this equation? Basically for testing we get ut as usual, and then we regress ut on other lag parameters, and then we do LMR t square. However, if we put a restriction on higher order parameter, it suggests if improvement of power properties is required through a Taylor series. Okay, so it's good to impose restriction on any higher order, right? And that is what is this equation, this example is about, sampling properties of LST. Well, we are dealing with this problem. Monte Carlo simulation will be done to estimate the parameters first, where d is unknown, intermediate lag is y square minus d. We have this cubic equation as we are familiar with, and then loss in the power of the test statistics is tested with excluding one order. This is setting 0 and rest is not 0. So this is in a nutshell what we are doing. So let's see what we are about to do in this equation, in this problem. Let's get back to 37. So exactly the same equation, right? But we have some initial values that we need to see. So t is equal to, first we'll do it 100 observations, then we'll 200 observations and see the consistency. That's all. Let's start with that. But first, in simulating the threshold models, we need to specify our functions, local functions. So obviously, because we are gonna do some simulation, we'll start with set seed, and we'll start from there. So the first is simulate a threshold autoregressive model, and as we can remember, the parameters are all the phi's from the region 1, betas from region 2, then adjustment, threshold and variance, speed of adjustment, threshold and variance. So tar G type number of observations, phi 1, beta 1, this is one parameter, gamma C significance, G type and number of observations, right? Now G type is something coming from the threshold models themselves. So we are saying G type is this equation, weighing function, or this is the G type equation, or omega t can be something like that. We want to estimate number of observations too, right? Because well, those are the inputs, right? Those are the inputs and output. So we will input G type and number of observations, and this function will generate so omega and number of observations. All right, so let's see. So 100 observations will be estimated. So the first 100 will add to our total number of observations. 35, 36. So you'll add to the total 100 observations. So we have 100,000 replications to do. So you'll add another 100, and then we'll do linearity test. which we will deduct at the end, so there is not a problem here. Okay, are we recording? Yes. So start with set R. When the G type is 1, so we will pass, in our term module we will pass to what type are we working on. Number of observations will pass. The initial values are given to us, that those we will pass. We will input these, all of these, right? Gamma, C significance, these are all given to us. So number of observations plus 100. G type is when the first G type is there, which is the threshold model. Let's get back to the threshold model. Sorry for jumping around a bit, but this is very important to understand each step. Yt minus 1 is greater than threshold. Well, yt minus d, c, from infinity to d, c to the power minus c. So we want to see if our yt minus 1, well, the omega will be yt minus 1 greater than threshold. If G type is 2, so in the meantime R, okay, random number, generating random number of observations 100 times, replicate 0 for to 100,000 plus 100, right? 100,000 plus 100 to number of observations, because this is a AR1 model, so S plus 1 2. Let's not think about the loop here to begin with. Let's start with the if logic. If we pass 1, then G will be yt minus 1 greater than 0 from the equation. If we pass 2, then G will be normal, distribution, cumulative distribution function, gamma multiplied to yt minus 1 minus c. So gamma yt minus 1 minus c. So d, delay is 1. That is something we are assuming. G type equals 3 when well, if we pass that, we are experiencing this one. When we pass G type equals 3, we expect y divided by 1 plus exponential of yt minus 1 minus c. So this is just normal distribution of p norm. Okay, normal distribution is p norm, gamma yt minus 1 minus c. Then this is L star, so set R. Oh, we started with set R, that's why we started with set R. So yt minus 1 greater than 1, simply. So yt minus 1 greater than c. G type is, if you 1, then yt minus 1 greater than c. Then star, if is 2, then normal distribution of exponential of normal distribution of gamma yt minus 1 minus c, this one. Okay, star. So p norm into gamma yt minus 1 minus c. Then G type 3 is L star. L star is 1 divided by exponential 1 divided by 1 plus exponential of gamma yt minus 1 minus c minus exponential of gamma yt minus 1 minus c. Then comes S star, G type 4. S star is 1 minus exponential of gamma yt minus 1 minus c squared, right? And so if all these, and then we end with the actual equation 5 yt minus 1 beta 1 yt minus 1 g. Okay, that is the actual equation. So what was our actual equation here? So 5 yt minus 1 yt equals 5 yt minus 1 plus wt multiplied to this, so g into beta 1 yt minus 1. So if this is beta 1, right, beta 1 yt minus 1 g into sigma multiplied to variance multiplied to ut, because sigma has been simulated already, sigma into ut, and then we trim the first 100. So all these end with a loop. 2 is equal to number of observations plus 100. Okay, 2 is equal to number of observations plus 100. So this system is returning y. So the vector y for 100,000 times this system, but depending on what type of model, threshold model we are passing in, this system will return you y, trimming the first 100 for 2 to number of observation plus 100, and that is the function. Simulate a threshold autoregressive model, a simulated threshold autoregressive model. Then I'm talking about LM statistics to test a threshold autoregressive model assuming one lag in the auxiliary model. Okay, so let's move into that. And what are we estimating here? Let's move down. So now it's testing, and we need to remember what are the, these are the parameters. Have we defined any log likelihood function in this equation? No, maybe it's not necessary. Okay. Let's do some LM statistics. First stage regression, second stage regression. So let's do the LM statistics testing. And what are the stages? Regress y on yt minus 1 to get the restricted residual. So LM, our outputs will be LM and degrees of freedom, and y var and p will be our inputs. Y variable and p, only these two are our inputs. Function y var p. So first stage regression, we take y and we have estimated y. We take y and trim it. We take the level, and x is 1s and the lag. We're preparing this for regression. K is equal to size of x2, which is number of columns in x. So how many variables you have actually in a columns, that's all. And that might be usable later. And then we do residual. We find the residual through the regression. Second stage regression is u on all the lag parameters, right? So if p equals 1, so if we are talking about okay, so we will just move at a regular at a recursive stage. If p equals 1, x is equal to x2 multiplied to x2, second stage regression. Okay, we are considering our lag yt minus 1 as x, yt minus 1, yt minus d, yt minus, so beautiful. Okay, because the second one will continue to increase in a squared manner. Do you remember that? Yeah, let me show you. See, this is the equation. Yt minus 1, yt minus d, yt square minus d, yt cube minus d, that will continue. It's kind of like, Hadamard product. It's kind of like Hadamard product, but it's not that. So let's see how it goes. So if p equals 1, second stage regression, because we are doing 1 by 1 regression, that's why we are doing p. Regress u on 1 to equals 1, then x. If p equals 1, okay, then x is where column bind x, then all elements to element by element Hadamard, which is kind of to x, and okay, it's better I'm just gonna follow this equation to explain. Yt minus 1, yt minus d, so x and x squared Hadamard, just like Hadamard, x and x just multiplied. If p equals 2, then x2 multiplied to x2 to the power 1, I mean the second element, then x2 multiplied to x2 squared. Second element is being played, right? How many elements do we have? How many variables do you have? We have just 2. Basically, yeah, because we are only stuck with the second element here. I think the second element matters, which is the lag of x, right? Okay, this is the lag, this is once, and this is the lag. So lag square, yt minus 1, yt minus 1 squared, then yt minus 1, yt minus 1, again yt minus 1, yt minus 1 squared. Okay, now it's fine. Yt minus 1, yt minus 1, yt minus 1, yt minus 1 squared. D, if d equals 1, then yt minus 1, yt minus 1 cube. Then comes v equals 3, which is lag p. Then x, then x2. So yt minus 1, yt minus 1, yt minus 1, yt minus 1 squared, yt minus 1, yt minus 1 cube. Then when lag is 4, yt minus 1, yt minus 1, yt minus 1, yt minus 1 cube. Why? Because the last one is yt minus 1, yt minus cube. Okay, fine. Is being cubed here when p is equal to 4. Because square, there is no square required in the last one, so is cubed. This one, p equals 3. When p equals 3, then we have this, right? I equals 1 to p equals 3. Have we gone up to p equals 4? Probably not, because this question suggests how many lags? 12, right? Let's come back to it again. 36. Just 2 lags, right? Okay. All right. So this is how we suggest. This is a bit of trick, and I couldn't figure out why we end, because it could have been gone up to 4, but it didn't. Okay, because square element is not here, probably because we are putting restriction, because we're going to put restriction on this one and make it 0. That's why. So this is the Taylor series. We just represented the Taylor series here in the equation, and we might want to put pi2 equals 0 and column bind. The in R we do it else if. So see, else if in R is separated, in MATLAB else if is joined, and there is no beginning. I mean, there is nothing beginning, so it doesn't really matter where it ends or begins. Else if column bind, we're doing column bind in columns, else if fine, and there it ends. Residual is e equals u minus x. Residual is simply regressing u on x, so we have u, regress u on all the lags, not x, don't be confused. Regress u on all the lags. It should have been y lag. And we take the residuals only. So you have these two, and then you do LM statistic, which is 1 minus summation of v squared divided by ut minus u squared. So v squared divided by u minus mean of u squared, that is the LM TR square equation. LM is, so this is the R square equation, 1 minus sum of u squared divided by sum of u minus mean of u squared. then lm is length of y, tr squared. So we have r square and then tr square, and degrees of freedom is the number of column you have minus, well, number of column you just generated minus actual number of columns in your input in your while x, that is degrees of freedom. So this function returns what? This function returns lm and degrees of freedom. So you have two local functions generated, and one is threshold function and one is the testing function. Now let's go back to our main equation, and what do we see in our main equation is that we are gonna use the L star, okay, and we have defined this in the function p is equal to 3. Is that something we're gonna call? And then we have these values given to us: c, phi, beta, gamma, sigma, number of observation, number of draws. So initialize array will what we are trying to do here, let's see. Okay, so we are gonna call for a L star model, I mean the function, we want to call the function, but again the function is based on this. This is the function, right? I is equal to 1 to j equals 1 to rho. So this is the augmented regression equation that we are calling for this threshold model. And for that, first we want our lm to have because we are also calculating the power, so we have our lm to have the size of 100,000 replications. We want powers to be the size of 100,000 application. So size of beta 1, okay, size of beta 1, and who is our beta 1? Beta is actually our parameter that we are estimating. By beta I'm talking about all the parameters, I guess, right? Let me check in the equation though. Phi 1, beta 1, phi 1, beta 1. What are the unknown parameters again? See, betas, because here you have the betas. Okay. This is the equation where I am following the size of beta. So it will, j will be from 1 to beta. Beta becomes in the column given in the column. Test is 4.36 given the column. Headed beta equals 0, which is close to nominal size. The size adjusted power function increases monotonically as beta becomes more positive. So beta from 0, we want beta goes to positive. That is the basic. And so we'll start with beta 0 and going to positive. J equals 1 to row, I equals 1 to row, so rows and columns. So first set the rows. 1 to length of beta, sequence of beta for j, sequence of beta, and for k, sequence of n rows. So length of beta is length of columns, because beta are the parameters, in total parameters that will be estimated. Number of draws is the rows. So first column j, then row, and the L star model. So call the function first that you have just generated, and also call the test, tar test, where this will go for t, where lm is residual and degrees of freedom is, so lm will go for t. We need t lms. Degrees of freedom, we don't need t lms. Degrees of freedom, so t is k here, right? The rows. and then let's set the size. Okay, in this example, simulating up to an L-star model was easy. Doing the power, which is the question asking, the power of the test statistics is what we are looking, because we want to find if there is a loss in our power. Let's have a look into the question again, because I'm a bit confused. Up to this was very easy. The threshold model development, estimation of the model was easy. It was not difficult. However, I want to see consistency property of the test, where power function 5% power function. So we're doing linearity test. So we want to see if our thresholds are linear and when would they converge. That is the basic, right? So what will be the power when power function size adjusted LST linearity test is in the size adjusted power function as a size of 5% and size adjusted power function 19.10, right? Going back and forth to 19.10, did I check? So okay, this is 19.10.